Hello Honors Physics students, let's get started here. Problems 9 and 10 on your notes page called Magnetic Forces. Now I try to make it very clear in the Google Classroom post, that's what you're looking at here, but still some students may have gotten confused. So the big curved object in these pictures, that's a horseshoe magnet. Here's one end, here's the other end, which means either the top or the bottom is the North Pole and the other one is the South Pole. It's like a bar magnet that's been curved into this horseshoe shape. And there's a wire with currents running down the middle of it, and then you can see that depending on which way the current is pointing, there's a magnetic force on the wire. And your job is to find the magnetic field of the horseshoe magnet. As I mentioned in the Google Classroom post, the wire itself, of course, has current, and yes, it does create a magnetic field, but that's not what we're doing here. And even if I hadn't said that, it's sort of implied because the wire experiences a force, and wires with currents only experience magnetic forces when there's an external magnetic field, and that's what you're trying to find, the external magnetic field created by the horseshoe magnets. Okay, so then it comes down to how we're going to do that, and of course it's going to be a right-hand rule. But now that we've been practicing with the right-hand rule, we want to make sure we know which one we're doing. Is this going to be the pointing one or the grabbing one? Okay, well, pointing one is for force and grabbing one is for field. So you say, oh, we're finding field, we must be doing the grabbing one, except that's not right, because the grabbing one is for field produced by a current-carrying wire, and I just got done saying we're not doing that, right? We're finding the external field produced by the horseshoe magnet. So if you did this problem by grabbing the wire, you did it incorrectly. So right now, pause the video and try it again. Okay, so you still need to be a little bit confused. So I know it's a little bit tough to see here because we're seeing everything in 3 dimensions, and that's one of the challenges in magnetism. But the magnetic force here in this number 9 is sort of pointing away from the magnet. If you can imagine, if you're looking head on to the magnet, this wire would be forced away from you. And this one here, this is the wire being forced, I should say, away from here, towards you here, excuse me, away from here, sort of towards the magnet. So this one is sort of jumping out towards you, and this one's sort of jumping away from you. Oh, sort of like what we did here in electricity and magnetism activity, where we have a horseshoe magnet, and we have this wire. This section here, the wire is the wire that's in between the poles of the magnet, and this then got forced away from the magnet or towards the magnet. That's really what we're looking at here, okay? So in number 9, you're doing right-hand rule, but it's got to be the pointing one. So your pointer finger should point, in this case, sort of to the right. That's the way the conventional current is pointing. And then your thumb is the force. So it's like right-hand rule in reverse. So you got to orient your hand so your thumb is now pointing out of the paper or out of the screen if you're doing it that way. And then you just curl your fingers whichever way is natural, and you should be getting to the top of the page. So this should be the direction of the magnetic field produced by the horseshoe magnet. And if that's still bothering you now that you see it, try the right-hand rule. So point your right hand, your pointer finger to the right, twist it until you can curl your fingers up, if you want to think of it that way, or towards the top of your page, and then you stick your thumb out, it's going to point out of the page. That's what's happening. This whole wire is being forced away from the magnet. It feels a force out of the page. What direction did you get for number 10? Well, again, charge is moving to the left, so your pointer finger to the left, and now you twist your wrist so you're pointing away from you or into your paper, because this wire is being forced towards the magnet, and when you curl your fingers, you should be getting to the top of the page. And now that you see it, again, if you're having some confusion here, try it. Point your finger to the left, curl your fingers to the top of the page, you should feel your thumb is pointing into the page. This wire is being forced away from you towards the magnet. Now notice, both these have the field pointing to the top of the page. Well, that should make sense, because if this is the same magnet, why would its field change? In fact, we know one end is north, the other end is south. Go ahead and label the poles either north or south based on the rules we have for magnetic field lines. Pause the video and do that. So we should be getting the bottom pole is north, the top pole is south, because magnetic field lines point from north to south. From north to south. The same magnet, of course its field doesn't change. We should be getting the same answer for both, going right back to the activity you did, right? Can you imagine that for this picture number 9, we're looking at this picture head on. This part of the wire has charges moving this way, which is to the right if you're looking at it head on, and it jumps away from the magnet, feels a force away from the magnet. That's what's happening here. In this situation, we reversed the leads. Now the charge is moving the other way, which is to the left if we're looking dead on to this magnet. And here, the wire got forced towards the magnet, which is what this picture is showing here. But notice that I've not changed the poles from picture to picture. Here's the North Pole, here's the North Pole, here's the South Pole, here's the South Pole. No matter what, if the magnet hasn't changed, then its field hasn't changed. By changing the direction of the current, that changes the results, which way the current feels a force. Alright, let's go on to number 27. Here we have another wire with current, and you've seen a picture like this before, and it's drawn in 3 dimensions. These charges are moving sort of away from you or sort of into the page. And so we want to find the magnetic field. We know it's going to be right-hand rule. So is this the pointing one or the grabbing one? This is the grabbing one. This is one where you grab the wire because we're finding the field from the current. Alright, so you orient your fingers or your thumbs so it's pointing sort of into the page, away from you. Wrap your fingers around. Remember, I like to do it with an actual physical object, so make sure you're grabbing a pencil or pen. And we should have a field line that looks something like this. On the right-hand side, it's pointing to the bottom of the page. On the left-hand side, or behind the wire, if you think of it that way, it's pointing to the top of the page. And then it's always a good idea to maybe draw a couple more field lines, maybe clustered in closer to the wire, farther away, more spread out farther than the wire, because we know, of course, the field weakens the farther you get from the axis of the wire. A lot of times we draw this with dots and X's. You can't really do that here, because if you are looking sort of in 3 dimensions, if you were going to try to orient your pen or pencil, your pen or pencil is going to be sticking right up. It's going to be like, standing up, if you want to think of it like that way, sort of balancing, standing up on your paper, and you wrap your fingers around. At no point do your fingers ever hit the paper or come up out of the paper, so you can't really use dots and X's. You can only really do this with circles. Okay, let's get into some of the questions from the textbook in Cutnell and Johnson. We'll start here with conceptual question 4, which asks how you could orient a current-carrying wire inside a magnetic field to feel no magnetic force. And hopefully you said something like this. It's going to be placed so its length is parallel to magnetic field lines. You didn't have to say those exact words, but something like that. And of course, as always, we look at an equation. This one is F sub m equals ILB sine theta, because we're talking about a wire with current, and we need the magnetic force to be 0. So we need sine theta to be 0. That means that either theta is 0 degrees or 180 degrees. So either the charge is moving with the field or against the field, it experiences no magnetic force. But then you say to yourself, well, what about the other terms? Could I be 0? Well, of course it could, except the problem said it's a current-carrying wire. So no, it actually can't be in this case. You can't say I equals 0 because it says there's a current in the wire. What about B? Could B be equal 0? Well, yeah, of course. If there's no magnetic field, there'd be no magnetic force. But the problem says there is a magnetic field, so you can't do that. So, it's good if you're thinking about that, but then you have to. So you're getting the idea of, looking at the algebra of the problem, but you have to look at the actual problem. And what about L being 0? Well, yeah, I guess, but then there's no wire, right? There's no length. That doesn't make sense. So you're getting the idea if you're thinking about any of those being 0, causing the magnetic force to be 0, but they don't have physical significance in this particular question. Let's look at focus on concept number 16 from Cutnell and Johnson. We've got all these arrangements of wires we want to find, which gives a 0 net magnetic field at point P. We'll just evaluate each situation in turn, and then at the end see which choice makes the most sense. Alright, so we're finding the field from a wire, so of course this is going to be a grabbing situation, and so first I'll always go top and then bottom. So for the top wire, if you want to follow my advice, you put your pen or pencil right up against your paper, you have your thumb pointing to the right. We've already done a problem just like this before last class, and then you feel your fingers hitting the paper below the wire, which means that its field from the top wire is going to be pointing into the paper. It's a very physical thing, right? Make sure you're trying this. Make sure you're actually trying to grab that wire. You'll feel your fingers hitting the paper. That means you're sort of trying to poke into the paper. That's a field away from you. Now this one has the charge moving the other way, so again, try to grab your imaginary wire, try to put your pen or pencil on the paper, and now your thumb is pointing to the left, and when you try to grab your wire above here at where point P is, you can again feel your fingers hitting the paper. That means the field from the bottom wire is also into. So could those give a 0 net magnetic field? Well, no, they're added together. They're pointing in the same direction, so picture 1's not going to work. Alright, picture 2, the top wire is exactly the same, so at point P, obviously we know it's going to be into the paper. The bottom wire has the charge going the other way. I imagine you already know what's going to happen, but try it. If you're following my advice, you take your pen or pencil, put it up against your paper, then lift it up just slightly, so as you grab it with your right hand, you can curl your fingers underneath, and you stop in this region when you're sort of above the wire, if you want to think of the plane of the paper, and now your fingers are pointing up out of the paper, which means the magnetic field from the bottom wire is pointing out of the page. Could these two cancel? Well, yes, if they're carrying the same current, and point P is right in the middle. In fact, they absolutely will cancel, because D's the same number, right? The distance, or I should say R, excuse me, R is the same number from bottom wire to top wire, and of course I is the same, and everything else in the equation for B is the same, which means these two will cancel, so picture 2 will work. How about picture 3? Alright, so now we have the charge moving to the left, we have our imaginary wire sitting on our paper, you lift up just a little bit, so when you grab your wire with your right hand, your fingers curl underneath it, and then in this region below the wire, our fingers are poking up out of the paper. From the bottom wire was the same as this, so our fingers are poking up out of the paper. Can these two cancel? No, they're both pointing out of the paper. They can't possibly cancel, so picture 3 is out. Picture 4, alright, so here's our wire with charge moving to the right, and so it's the same as situation over here. That's going to be this situation, and feel free to try to grab your wire if you want to verify it, but really it's the same as 1 and 2. Alright, so we know it's into the paper. Here's a little bit different now. The charge moving to the bottom of the page, so put your pen or pencil on your paper. Try to grab with your right hand, your thumb pointing towards you, toward the bottom of the page. You're going to have to lift it up a little bit, so curl your fingers underneath to get to this region over here, and your fingers are poking up out of the paper, so it's out. Can these two cancel? You bet they can. They're in opposite directions, and point P is equidistant from the two wires. So in this case, it's pictures 2 and 4 because we have the fields in opposite directions. So in this case, that is choice A.